All right, so hello, we're going to look at related rates here in this video. So just getting started uh, looking at that topic. So um, this is a pretty challenging topic for students. You might think of these as just as word problems. Folks say are applications, or I don't know what it might be, but it's a certain type of problem, but it's not the same thing every time. So it's not like, computing a derivative using the product rule and use the product rule, and you know how to do that over and over again. It could be different because different functions, but you know what to do. This, it's much more, every problem is unique type deal. So there are some things that are generally true. So generally speaking, for a related rates problem, the setup is you want to find how a quantity is changing. So changing, think derivative. And it's changing with respect to time. So something d something dt. And the part of the setup is you know how this quantity relates to another quantity that's maybe easier to work with, where you either know its rate of change because it's given to you, or at least it's easier to find. So that's the setup. Our approach, once you have that set up, is you're going to have an equation that describes the relationship between them. You're going to differentiate both sides of the defining relation between the quantities with respect to time. So d whatever dt. And so when you do that, you're not going to have t's floating around anywhere, but these quantities are changing with respect to time. So you're using the chain rule that, things are kind of hidden in some sense, but they're functions of time. So you're going to have an equation there, and you got some d something dt's and some variable names and all some stuff floating around, and basically you're going to have values or known values for everything there except one of the rates of change, and that's the one that you're trying to find. So you plug in the values, and you get that rate of change. You figure out what it is, and that's solving the problem. So not too hard to state, but these do very much get complicated and tricky for folks until you get the hang of it. So like I've kind of been saying, all these problems are different, so there's no one algorithm that'll handle every case, but you can have kind of a general problem-solving strategy, which could be modified slightly to be a more broad problem-solving strategy, but we've got some things in mind that are specific to related rates problems. So here's the strategy. First of all, step one, read the problem. Don't zip through it. Read through it carefully. Look at sentence by sentence. Figure out what are we looking for, what are we trying to find, what are we given, questions like that. Look at units if there are any that can tell you some information. Draw a diagram, especially with these problems, but in general for word problems. Kind of seeing the picture can help you set up and establish the relationship between the quantities, between the unknowns, as it were. Introduce notation. So you've got your picture drawn. You're trying to figure out whatever you're trying to figure out. Some of the things are going to be unknown, so bring in some notation. If you got an unknown, maybe x makes sense. Maybe it's the height of something, so you say h for that. Bring that notation. And then you want to express it in terms of derivatives. There's going to be some rates of change there, so you want to know how the volume of a spherical balloon was changing. You'd be using language like dv dt, right? That's what we mean there. Then you want to have an equation that relates to quantities. This is probably the most important and kind of the trickiest part, because that's what you're going to use to figure out your solution. Now, the quantities in question, they're going to be quantities whose derivatives are either given to you or the thing you're trying to find. So if I want to see how volume is changing, I better have an equation that involves volume. Once I've got that, differentiate both sides of the equation with respect to time, and then substitute to solve for the unknown rate, the unknown rate of change, the unknown derivative, if you like. So the related part has to do with the equation that relates to quantities, and the rate part has to do with the rate of change, derivative. So here's an example. I've got the radius of a sphere increasing at a rate of 1.5 centimeters per minute. So some things I can make, some notes I can make along the way. That's a length. That's time. That's good. So my derivative is length per unit time. It's always going to be per time because for these problems, these quantities are changing with respect to time. At what rate is the surface area of the sphere increasing when the radius is 100 centimeters? So first of all, let's think about what I've got. I'm going to do my best to draw something like a sphere here. So there's my sphere, alleged sphere. And the radius is increasing at a rate of 1.5 centimeters per minute. So I've got something to do with the radius, so let's try to mark that out. We'll call that R. What else can we say? Maybe that's about it for now. So let's kind of make a list of what we know. Let me actually start with what I want. I want to find what rate is the surface area of the sphere increasing when the radius is 100 centimeters. So let's say S equals surface area. Say R equals the radius. So I want to find ds dt, the rate of change of the surface area when R equals 100, and that's centimeters. And I know that the radius is changing at a rate of 1.5 centimeters per minute. It's increasing, so it's positive 1.5. So I've got dr dt equals 1.5 . What else do I know? I guess that's about it. So how do R and S relate? That's my question. So I'm not going through these steps necessarily 1, 2, 3, 4, 5, but I read the problem. I got a diagram to help and bringing in some notation for things. Expressing in terms of derivatives, using that information that I've been given along with thinking about what I want to find. And now I'm kind of up to this point where I have an equation that relates the quantities. So I've got the surface area of the sphere and the radius of the sphere. So sometimes you have to look up these things, but you might remember here, surface area of a sphere of radius r. Boy, that's terrible. Terrible handwriting. Surface area of a sphere of radius r. So its surface area is 4 pi r squared. That is the equation that connects, that relates these quantities that I don't know, r and s. So I figured this out. Now I need to differentiate, and I'm going to differentiate with respect to time. So now, differentiate. So both of these, both surface area and r, we're thinking of them as functions of time, even though we don't see t's in there. But what that means is we're going to use the chain rule. So here, derivative of s, it would just be 1, then times ds dt. So just ds dt equals 4 pi times, this is just a constant, 2r dr dt. So, putting everything together, rate of change of the surface area with respect to t is, kind of cleaning things up, I could take 4 times 2, we'll say 8 pi r times dr dt. I want to know what's happening when the radius is 100 centimeters. So that means the instant in time when r equals 100. Or if you like, keep it in mind, centimeters. What we said earlier, a couple slides back, I'll keep it on this slide, but we said this bit of information tells us that dr dt equals 1.5. So plugging those in, I've got when r equals 100, ds dt is 8 pi times 100, emphasize that for r, times 1.5 from up here. So 1.5, I don't know how you want to do this. I might do 8 times 1.5, 1/2 of 8 is 12. So it looks like it's 1200 pi. Maybe that number doesn't mean a lot to us. Some of these things are kind of difficult to interpret when we're not used to the units, but that is our answer. The other thing I want to keep in mind is I'm looking at how surface area, that rate of change. So surface area's area would be area unit per unit time. And if we look, this 100, remember, was in centimeters. This was in centimeters per minute. So this is going to be in square centimeters per minute. And so the units match up as well, and they make sense. Alright, so it's hard to know if that number makes sense. For a lot of problems you'll see, it might only make sense whether it's positive or negative to tell you if you got an idea if you did it right or not. But we did do this one right, and it is tricky. So again, you want to follow these steps, not exactly one, exactly two, but just that general kind of plan of attack. Sketch what it is you're looking at, label things, figure out what am I trying to find, what do I know, how do I connect them, and just with basically you're just going to need practice. Every problem is going to be different, but they've got a couple general principles that are the same. Trying to find a rate of change is the big idea. So we got the short problem description, got this example, tried to be thorough, probably too wordy, but I hope this helps kind of get you on the way to starting to make sense of these problems. They're really not too bad with some practice, but you do need practice with them.